So very good morning, everybody. My name is Anushka Dassi,
And I'm Pinakin Choudhary.
and we'll be presenting the Gödel's paradox of incompleteness. Uh, in the early 20th century, when Gödel's paradox came about, it made us question the very foundation of mathematics. It shook the belief that mathematics was concrete. It shattered our belief, shattered our dream, in fact, for a more complete and consistent formal system. So, what was it? Was it a set of axioms, theorems, bulky, hefty Greek symbols all put together? In fact, no. Its simplicity was a derision to the fragility of mathematics. It was just one line, four words, at the core of what broke mathematics. This statement is false. If this statement is false, then in fact this statement becomes true. And if this statement is true, then that implies that this statement is false. Earlier mentioned, it is a self-referential paradox.
The Gödel's incompleteness theorem is like quite a breakthrough in mathematics. But I think the history, the journey that led to it, which is filled with paradoxes and contradictions and formalization of the mathematics, is also quite important. So mathematics basically started with Babylonians and Greeks, and what we've been building for more than 2000 years is that we have a set of axioms and there are rules of inference. And from that we can derive the theorems, and this kind of builds into a system. Now, this gave rise to Euclidean geometry, which is based on a few axioms, number theory, and algebra. Now, the thing in 19th and 20th century was there were non-Euclidean geometries, and there was Cantor who sort of questioned the nature of infinities. So people started questioning the basics of the mathematics. For example, uh, you have your Euclidean geometry, but if you change a few of the axioms, you get a new geometry, and you can't call it wrong because there are certain rules of inference from which it is derived, and it's quite correct. For example, on a spherical surface, the geometry would be different than what we normally think it is to be right. So, mathematicians started to view the subject as a collection of self-consistent stories or systems, and like none of them could be given special status because they are all correct and to themselves. After that came the formalist, Hilbert being the most prominent of them. So Hilbert was basically he thought that like mathematics could be just described in terms of a finite set of axioms. The finite is the important word here. So we can just describe all the mathematics with finite complete set of axioms and derive the every mathematical aspect from that. So he claimed that the system would be consistent, there would be no loopholes in it, and it can every complex mathematics can be reduced to some basic arithmetic. This was Hilbert's program, and it was quite similar to what physicists thought. The theory of everything. That there's just one theory, and like all of the physics can be explained to that. Now there were obviously hurdles on the way. For example, the first one being the Russell's paradox, which was the first paradox we explained today. The set of all sets that don't contain themselves. Now, as Naman and Indra Yud explained, this is quite a beautiful paradox. It is also related to the Barber paradox, which Russell gave himself, that Barber only shaves people who don't shave themselves. So, does the barber shave himself or not? So, all of these rise from self-referential statements. So, there are many forms of it. It started like 2000 years ago. People started noticing that self-referential statements at that time in Socrates, who said, I know that I know nothing. So, well, he knows something that he doesn't know anything. So, that's quite of the paradox right there. And these self-referential paradox and infinite loop were also like in art and music. Even Bach like produce music, that was kind of a paradox in itself. We can't tell if it where it started, where it ends. And this is a painting by MC Escher, the waterfall. Here you can see the waterfall. It falls, but it's like it seems like it doesn't have the life.
So moving ahead to what the theorem actually states and how can we provide what is the viable proof for it. There are a couple of terms that we'll be mentioning. Firstly, what is a formal system? A formal system is basically a set of axioms which are put together, binded by rules of inference, and they help us in proving theories. Now, as it was mentioned earlier, it is very important that the number of axioms in the system are finite. There can be numerous algorithms that can be used to generate such axioms. Completeness of a formal system is basically all the statements in the formal system have to be provable. Consistency states that a formal system is consistent if there are statements that are either true or false. There can be no statement which is both true and false, and there can neither be one that is none of them. When we are considering Gödel's first theorem, we consider consistent systems. For the first incompleteness theorem, the statement for it is that any consistent formal system F within a certain amount of arithmetic is incomplete. Now, when Gödel made this statement, it was not merely a claim. It was backed by methods of his provability, which showed there was a relatively simple statement of number theory, which showed that this actually holds. Now, there's a common misunderstanding regarding this theorem that it shows that there are truths that cannot be proved. While Gödel's incompleteness theorem is basically, it does not talk about provability in an absolute sense, but it rather references to it in a more relative sort of way. As we have seen, and it was mentioned by the earlier presentations as well, that ZFC, that is Zermelo-Fraenkel axiom system, including the axiom of choice, is one of the most important and most powerful tools in arithmetic, which is used to prove statements. And here, Gödel's first theorem gives us arithmetic truths that cannot be shown by ZFC. To move into it, we also focus on Robinson or Q arithmetic systems, which are based upon 7 axioms, as I mentioned here. The first axiom states the x dash that is there, which implies that the successor of x. So the first axiom states that 0 cannot be the successor of any element that is present in the system. The second axiom is based on a one-to-one system, which states that if the successor of x and the successor of y are similar or are equal, this would imply that x and y are equal as well. The third axiom is based upon the fact that either an element in the set is 0 or it is a successor of some other element. And the next two statements are based on the recursive definition of addition. The last two are based upon the multiplicative definition, recursive definition of multiplication. And here it is shown this is the inductive axiom. Upon adding this to the 7 axioms, it gives rise to the piano axioms. As first year undergraduates, this gives us a lot of memories back, how it started. And so a certain amount of elementary arithmetic is a very important part of Gödel's theorem, and this can be fulfilled by Q arithmetic system. Now, although theories are not here interpreted in the language of arithmetic, but there is something called interpretability, where, for example, we have one theory, let's say T1, and we have another theory called T2. If T2 contains and can define appropriately all the primitive components and the range of T1, then every theory, then T1 can be perfectly explained through T2. That is what interpretability of these theories shows, and Gödel used a method. Gödel used this method for proof of this theorem. It preserves elementary formal properties of theories which are very important to us, such as consistency and completeness of theorems. The Gödel numbering, which is a system of how he provided mathematics to speak for itself. Here, the process is like 0 is equal to 0 is a statement. 0 is represented by 6 in Gödel numbering. Equal to sign is represented by 5. 0 is again represented by 6. Now the value of these symbols is raised to power to the series of prime numbers. So 2 raised to the power 6 into 3 raised to the power 5 into 5 raised to the power 6 will give us 0 equal to 0 according to Gödel numbering. And all statements could be represented in such a manner, even the false ones. The special one, which says that this statement cannot be true, was represented using a Gödel numbering called G. So Gödel devised a way to represent these statements, because as it was mentioned that English is a natural language and it is very easy to create self-referential statements in it. While mathematics and arithmetic is consistent, either it is true or it is false. But here Gödel created a method such that these self-referential English statements could be represented using arithmetic. So this statement cannot be proved is represented using the special Gödel numbering called G. Now, if it's false, then there is a proof. But if we are able to prove it, then it becomes true. This symbolizes that this statement cannot be true, can only be true, cannot be proved. Sorry.
Sorry, can you go back? Statement is false, and there is a proof that it is false.
This is like unlike the liar's paradox, where it can't be true or false, that leads to contradiction. But this is not a contradiction per se. It is a contradiction only when if we consider it to be false. If it's true, then it leads to no contradiction. So that's it.
So although he did not generate a Gödel numerator, but brief idea of it was to create equations such as Pythagoras theorem and a plus minus a is equal to 0 into numeric forms. Now, this does not mean that complete formalized theories do not exist. Although there are incomplete ones, we also have addition and multiplication of positive integers and such, which devise a proof rather for the completeness of theorems.
Now you can think of it this way, like there is a set of axioms and Gödel says that the system is incomplete. So there exists a statement in that system of axioms which is true but unprovable. So you say we'll create a new system which has the set of axioms and we'll add this true statement as an axiom. So that system will be complete. But again, by Gödel's definition, that system also has a statement that is unprovable but true. So you can just go on like this, and spoiler alert, it's infinite regression, and you get a like infinite system of axioms for a system to be complete. So the Hilbert's aim to
It
this
will be a little precise. You get an infinite system of things for the system to be complete.
yeah the Hilbert wanted a finite set of axioms to describe all of the mathematics, but here we can see that it is simply not possible. You would need an infinite set of axioms, which is basically saying that not possible in a finite set of axioms. But like this can go on forever. So this is what I'm saying. Like the stairs. This is also a painting by N.C. Esther. These stairs always go up, but it seems like they are not like moving up, but they still go up.
They go up again, but then they come down.
Ascending, descending.
They start from the same level.
So, but still there's a catch. Gödel's incompleteness theorem, it doesn't state you can't prove a statement. It states that there exists a statement in this system of axioms which can't be proved. So there might be a different set of axioms where the statement is provable. So in this way, you can like create new branches of mathematics have been created for, and this led to a quite interesting new discoveries. So this is like Stephen Hawking in grand design he talks about model dependent realism. Basically, you have set of like in physics you have a set of observations and you get results. Now, you can think that maybe our observations are correct, maybe are wrong, maybe our sensors are not working properly. Maybe this is true. But what you need to think is that the results, the predictions after applying equations and all we get are correct. So we have to like stop somewhere and just accept the reality that maybe this model is the finite model. Maybe along the way, as better instruments come, we'll maybe find some errors, like Gödel's incompleteness theorem in mathematics. But there's still scope of new discoveries and much more.
So when Gödel's incompleteness theorem came about, mathematicians were in a frenzy. They thought that what if all their lives' work would lead up to nothing because they were working on something that could never be proved. So as we come to the end of this presentation, we would like to put this forward. That for now, what is important is not finding the answers, but at least looking for them. We would like to complete this presentation with an incomplete slide in the spirit of incompleteness theorem. Thank you.